Okay, good afternoon. Habit and objectives in chemistry in this forthcoming examination. So, as we promised that 2:45 we will set up. Sorry, we are a few minutes late, about 6 minutes late. But in today, I assume that you are there to bring your questions. It will be more interactive, and this guide is sure for this forthcoming exam for your theory and objectives as far as chemistry is concerned. So in that aspect, before we can continue, we pray that the good Lord will help us to understand well whatever we're going to do today and discuss in a very good way. Your live chat will contribute a lot in this. First, we will go with some past question, and from that you get the guide. Remember, this is a short guide and together we'll start. So this question here says, what is the structure of the atom as proposed by Rutherford? The structure of the atom as proposed by Rutherford. First, what we have here is a short guide on chemistry theory and objectives. So here they are asking us to explain Rutherford's atomic model. Rutherford's atomic model. From the question here, they tell us to explain this, but I will use this opportunity to explain other models of the atom, even J.J. Thomson model, the Nebel's model of atom. But we answer the one they asked us first. And as to Rutherford, the model of atom is in this way. Believe that atom is made up of central positive charge, nucleus, then surrounded by a cloud of electrons. He did not indicate that the energy of the orbiting electrons are quantized. It's a kind of a cloud of electrons. There is nothing like shell. So this is the real model of atom according to Rutherford, where here is the nucleus, which is positively charged, and here it represents cloud of electrons. So this is his model, that an atom is made up of a positively charged nucleus revolving around the nucleus. He did not quantize at all the electrons. So this has a limitation. The limitation here is that his statement was true, but the fault here is that if electrons which are negatively charged is revolving around the nucleus which are positively charged, we all know that unlike charges attract. So there is a tendency idea of an atom, and his idea, that's Nebel's idea, explained why atoms do not collapse, saying that electrons will never change their position unless they gain or lose energy, because any electron here is existing here because it possesses some kind of energy. It can only move in time, can be promoted to another level. For this electron to come down here, you have to remove the energy. So we have a lower energy, not that way, right? But orbit, that's the angular momentum is quantized. They don't just move in a cloud just like this. Then another person's model was J.J. Thomson. That was the oldest one among these three on the board. According to J.J. Thomson, he saw that the atom is a positively charged body. Positively charged body with negative charges embedded in it. This was John Joseph Thomson's model. This is J.J. Thomson's model. While this one is Nebel and this is a Rutherford's model. This was disproved wrong by the alpha scattering experiment, Gibbs and Muller alpha scattering experiment. The students of Rutherford, their experiment couldn't prove this correct, and that made Rutherford to now say that this is what atoms should look like and not like this. Because according to this man, if it is true, when they bombarded an atom with alpha rays, most of them passed undisturbed. Some were deflected at large angles. That is what made scientists to say that this model is wrong. So J.J. Thomson saw that this is what we call the plum pudding model of an atom. The plum pudding model of an atom is according to John Joseph Thomson. But the person that saw atom as a miniature solar system should be Rutherford and Nebel. Rutherford saw it as just where the nucleus is the sun, and the electron serves as the planet moving around the sun. But the difference is that it was not quantized. So Nebel's theory should be the best among the three. But Nebel have also some limitations. When we talk about Zimmer's effect, and equally the Hesbenge uncertainty principle try to give some limitations to this theory. Then we are done with the atomic model. If you have your questions, you ask there in the comment box. Then they said distinguish between the atomic number and the mass number of an element. You know that atomic number is actually the number of protons only in the nucleus of an atom. The proton only is just the atomic number. Then the number of proton and neutron in nucleus is the mass number. In other words, the mass of the nucleus is the mass number, but the mass of the proton alone is the atomic number. And remember that in a neutral atom, the number of protons is also equal to the number of electrons. So you can confidently say that atomic number in a neutral atom is equal to the number of electrons. This will be correct, provided you put neutral atom. But if you don't put neutral atom, your definition is faulty. You rather say atomic number is the number of protons in the nucleus of an atom only, while atomic mass or mass number is the number of protons and neutrons. And the proton determines the chemical property. Neutrons only add mass. So atomic mass is. Explain why the relative atomic mass of chlorine is not a whole. It's very simple, because chlorine is a mixture of different isotopes. We have chlorine 35 and chlorine 37, and their relative abundance is not equal. So after calculating, the average of these mixtures of these isotopes made it 35.5. That's why it's not a whole number. It's because of the fact that chlorine exists in different forms of isotopes. And remember what isotopes are. Then the next question says, what is meant by first ionization energy? Ionization energy. We are discussing first ionization energy. So first ionization, then energy. You should know that the common term, the word ionization actually means just the formation of ions, which is involving either loss or gain of electron. Then the energy spent in it should be ionization energy. But in this context, when an atom loses an electron, the energy change involved is called ionization energy. And for example, when sodium loses one electron, it will become oxidized to sodium ion, and this is actually oxidation. So the energy spent in removing this electron from an atom to form a positively charged ion is called ionization energy. Ionization energy, and they are first ionization energy, second ionization energy, and third ionization. You get it when you follow my explanation. Now watch this. There are atoms that don't have second and third ionization energy. There are atoms that only have first ionization energy, such that their second ionization energy becomes practically impossible. So in that aspect, let's use sodium. Remember, electron in chemistry, electrons lost are electrons in the last shell. Taking sodium for example, sodium have 2, 8 and 1. It is only this last electron that will be removed. It becomes practically impossible. The energy becomes so high in chemistry that you can't remove any electron from here, because it will achieve what we call octet stability. Then for sodium, the energy required to remove this only single lonely electron in the L shell is the first ionization energy. You don't have second ionization energy. Why? Because the energy becomes too high that it becomes practically impossible to do that. Then if you come to magnesium, which has 2, 8 and 2, that is where we can have first, second ionization energy. Now, the energy required, magnesium will lose these two. But the fact there is that this is what we have been writing. Mg minus 2E will give you Mg2 plus. This is just the summary. But in actual sense, magnesium will first lose one electron to give you Mg plus. So in this case, the energy required to remove the most loosely bound electron among these two, one is more loosely bound than the other. The energy required to remove the most loosely bound electron among these two electrons in the outermost shell of magnesium stands as the first ionization energy of magnesium. Then, coming back, remember now, by definition, first ionization energy is the minimum energy required to remove the most loosely bound electron. The minimum energy required to remove the most loosely bound electron from the outermost shell of an atom to form a singly positively charged ion, singly positively charged or unipositively charged ion. That is an ion that have a charge of +1 only. Then when magnesium plus loses another electron, remember here we are left with 11 electrons. Here it has been 12. For losing one, it remains 11. For this one that is now positively charged, losing another electron again, that's the second one, is now what we call second ionization energy. So second ionization energy is actually the energy required to remove an electron from a positively charged ion, singly positively charged ion, to produce a divalent ion. So when it has acquired +1, you remove again. The energy involved here is second ionization energy. For magnesium, third ionization energy now is very difficult because it now enters into the other shell. In chemistry, we only remove from the last shell. That is how chemical reaction is effected. So you can now see that first ionization energy by definition is the minimum amount of energy required to remove the most loosely bound electron from the outermost shell of an atom to form a unipositively charged ion. Unipositively charged ion. So here you have first ionization energy, here is first. Then, if for example magnesium have up to 3 electrons in the outermost shell, it is now possible to achieve the third ionization energy. So to illustrate that, aluminium is possible. Aluminium is number 13, and that shows 2, 8, 3. The outermost shell is 3. Then the inner shell, the other shell is 8 and 2. So these 3 electrons, all you know from before to them now is just aluminium minus 3 electrons will give you Al3 plus. No, this is a 3-step reaction. First, it should be aluminium will remove the most loosely bound to become this. It can never be stable. It will keep losing again to become Al2 plus. Then we have Al2 plus to lose another one to become Al3 plus. So here is first, second, third ionization energy. First, second, third ionization energy. That's it for that question. So, and remember in your periodic table, ionization energy decreases down the group and increases across the period. Decreases down the group and increases across the period. Then the next question here should be list 3 properties of electrovalent compounds. 3 properties. Is there any question so far? Anyone online?
Yeah, 4 people.
Okay. Please, if you have questions, I'm here. Use the comment box. That's the live chat, because your interaction matters a lot, please. Now, the next question says they told us to list 3 properties of electrovalent compounds. This is very easy. I'll be going straight. It is only your questions that can call me back. So if you sit back there, I wouldn't know what else to do. Remember, you can bring your questions within what I'm teaching or outside what I'm teaching, as far as it is in chemistry. Bring that question that disturbs you. All I know is that together we'll do it. This forthcoming examination is already a success. So, the electrovalent compounds we know are compounds formed from electrovalent combination, which is actually a combination that exists between metallic atom and a non-metallic atom. as we know. Their properties is this: electrovalent compounds are generally solids at room temperature. They are generally solids at room temperature. Means that ionic bond is a strong bond compared to covalent bond. Then number two, electrovalent compounds are actually they are, because of the strong bond, they have high melting point and high boiling point. Then most of them are good electrolytes. So electrovalent compounds are good electrolytes. They have high melting point and also high boiling point. Then they are actually polar in nature. That is, electrovalent compounds are polar in nature, and I told you they are solids at room temperature. The next question says, consider the following pairs of elements. I have here, okay, I is fluorine. I can't really understand this. Okay, I is fluorine and chlorine. Yeah. They gave us this. Remember, please, this is a guide. It's nowhere connected to any form of malpractice. So we have fluorine and okay, fluorine number 9 and chlorine 17. Then another pair, II is magnesium and calcium. That's 20, and here is 12. Okay, let's see their questions. They say, explain briefly why the elements in each pair have similar chemical properties. This is very simple. Explain in each pair why the elements, fluorine and chlorine, have similar chemical property. Magnesium and calcium have similar chemical property. The reason is because they have the same valency electron and they belong to the same group. I hope you are capturing it. They have the same valency electron and they belong to the same group. So fluorine and chlorine are actually what? Group 7 elements. They are the halogens and they all have valency of 7. Their outermost share is 7. Remember, elements in the same group share similar chemical properties because of the idea of similar valency. That's the element you can use fluorine, chlorine, bromine, iodine as starting. That's Football Club Barcelona International as starting. Of course, just learn. This is the cheat. Football Club Barcelona International as starting. This should be AS, I think, yeah, or AT, not AS. AS is arsenic. So this is the halogens. So that's fluorine, chlorine, group what? 7. But magnesium, calcium have the valency of 2. Magnesium is number 12, calcium is number 20. So you have KLMN282. Then calcium is Mg, this Ca. Calcium is 2882. What matters is that the last share 2. The same thing applicable here. Their last share is 7 and belong to group 7. So magnesium and calcium have similar chemical properties because they have the same valency electron, which is what? 2, and they belong to the same group, and their group is group 2. That is the alkali earth metals. For the group 2, you can use this acronym. You say be majestic, that's me teaching you. Can skills be real? That's be majestic, and skills be real. Beryllium, magnesium, calcium, strontium, barium, radium. This is group 2 element, 2 cheats on how to master the whole element in the periodic table. Write it by yourself. Okay, the next question now says,
someone is saying they have is on thermodynamics.
Okay.
Saying, please, can you revise it?
What aspect of the thermodynamics? Because in chemistry, as far as this class is concerned, thermodynamics don't usually come out, except we talk about exothermic, endothermic reactions. That's the only possible, and Gibbs free energy. So it's better if you can type any question concerning the thermodynamics, I will handle that. Or if you are lucky, if I see any question there, I will handle that. But the briefings I'll give you about thermodynamics is all about heat change. That is change in heat and chemical reactions. So you're supposed to know for the thermodynamics, you just know reactant. Then entropy change is also heat of product minus entropy of reactant. Then spontaneity of a given reaction. Need this, but without understanding it. Please take a look. If you react A plus B, initially A is cold, B is cold or normal, and eventually you feel heat. The reaction vessel feel hotter to touch. Such reaction is what? Exothermic. What does it mean? That the heat of the product is less than the heat of the reactant, and in that case it's going to give you a negative what? Sign. So the heat content of the product is higher, some part of it is. So in a simple way, if a reaction vessel feels hotter to touch, you call it exothermic reaction. Then if the reaction vessel feels colder to touch, you call it endothermic reaction. And remember, we are talking about the internal energy of the reactants and the products remaining. Understood? So eventually, if heat is given out, that's when you feel the hotness, it becomes negative. But when it is very cold to touch, it becomes positive. The common exothermic reaction you carry it out at home unknowingly. For you that is using detergent, ordinary detergent, that is the detergent based on labs, that's the one we call. This is also chemistry. Linear alkyl benzene sulfonoate. These are soapless, the basis for soapless detergent. If you add this, if you add water to this, it is hot. Some of you using all these commercial detergents, I won't call anyone here because none of them paid me for that. So all these commercial detergents in powder form, if you put it in your hand and add water, it feels hot to touch, and that's what we call exothermic reaction. And the hotness is mainly due to LABS, labs, that's linear alkyl benzene sulfonoate. And also, if you add water to this compound, which is common water softener they use in that, is also a bit exothermic reaction. But when you talk about your methylated spirit, isopropyl alcohol, in fact, almost all the alcohol family are cold to touch, and that's how they work. They disinfect by cold. They become cold to touch due to evaporative cooling. That one is what we call endothermic reaction. Then coming to the energy profile diagram. The energy profile diagram for exothermic and endothermic. If we have such thing like this, if you couldn't come back again to the origin and hang up, that is pure endothermic. Where here is A plus B and here is C plus D. But when it comes below where it started, let's assume it started here, the reactant, the energy profile diagram, this one is positive, negative, which is exo. Heat is released here, which means A plus B to give you what? C plus D. But look at another secret I have to give us now. This is if A plus B reacts to give you C plus D and it became endothermic. For C plus D, that's the reversible reaction. C plus D combining to give you A plus B will be now exothermic. Watch me. When we started, this is our reactant and here it becomes our product. To see why it is positive and negative, let's calibrate this. 0, 1, 2, 3, 4, 5. Let's see the activation energy as 6. In this case, if you trace well, you find out that this is heat. The heat of product here, that's HP, is 4. Then here, heat of reactants here is what? 3. And remember, heat change is equal to HP minus what? HR. In that case, it becomes what? 4 minus 3, which is equal to 1. And 1 is positive 1, is not negative. And that is why this reaction is endothermic. But when you consider the reverse here, if you reverse the reaction, know you now that I will now change the whole thing. Here becomes C plus D, and here becomes A plus B. This is the level A, still 4, yes? Then our product here is A plus B. So heat of product, HP here is 3. Heat of reactant here is 4. So what do you have? 3 minus 4, which will give you minus 1. That's why it should be exothermic reaction. So this is the possible questions that they may give to you. Then there's the there is what we call activation energy. Yes, in this energy profile diagram, the heat of product is 3. Sorry, the heat of reactant is 3. The heat of product is 4. But the what we call some amount of energy. So if you are asked between the energy of the reactant and the complex, not the product class, please. Which means if you are asked to find the activation energy here, usually denoted this way. If you don't understand this, let me write it well. Activation energy for this starts from 3 to 6 if the calculation is like this. So the difference now is 6 minus 3. So the activation energy here is 3. So if this is in kilojoule, it means for A plus B to be converted to C plus D, you must supply at least 3 kilojoules of energy to the system before it becomes converted. So don't make the mistake of saying 6 minus 4. It is not the difference between activation complex and the product. Rather, it's the difference between the energy of the activation complex and the energy of the reactant. So in this situation, if you are also asked to assess it, let's assume here remains 6. So the activation energy here is what? 6 minus 4, which will give you 2. So this one have lower activation energy. You should know that exothermic reactions have lower activation energy than endothermic reaction. That is why they usually tell you that exothermic reactions are spontaneous, because they require little energy. They can generate that little energy and proceed on their own. Being spontaneous means being able to happen on your own without external energy being supplied. Just the heat generated by the collision is enough to make the collision become more effective, such that the reactants are converted to what? Products. Is there any question so far? Okay. I hope we have any other person online still there.
5 people are online.
Okay, please. Thanks for being there. Remember, I'm here for you. Ask question, contribute here. Okay, then I think I'm still owing you in this aspect of Gibbs free energy. This free energy is very, very important. But before I come to that, let me also handle entropy. I have finished with a heat change. Heat change. And please, before I forget, there is a secret on this heat change. There is an equation they will write. You will know whether the heat change will be negative or positive. Like nitrogen combining with hydrogen to give you ammonia. That is during Haber process. In this case, balance the equation. There should be 2 here, and when 2 comes here, there should be 3 here. Remember, this is gas, gas, and gas. Haber process, that's the industrial way of producing ammonia gas. In this case, even if change in heat was not given to you, you should predict it. Look at the secret. Class, in any exam, heat change is only for forward reaction, please. Any heat change I will give you here is only guiding nitrogen combining with hydrogen to form ammonia, and not ammonia breaking down to form. Heat changes are for forward reaction. Simple. Now, even if on your own, will this forward reaction, will the forward reaction be exothermic or endothermic? Watch it. This is a gas, this is a gas. If you heat them more, if you keep heating gases, they will keep splitting, they can't join easily. So when you heat them, you are disfavoring it. Heating this system favor it, if not for rate of chemical reaction, which means heating disfavors it. And any reaction that heating do not favor is an exothermic reaction. So as far as this is concerned, Haber process is exothermic because of the fact that if you keep heating, the gases will be more apart. They can't form that bond between nitrogen and hydrogen. So, but the reverse is that if you apply coldness to, if you go and put this in a refrigerator, you can never split to hydrogen and nitrogen. Which means when you heat ammonia stronger and stronger, it will split more to hydrogen and nitrogen. So application of heat will favor backward reaction, which means backward reaction is purely endothermic. Okay, let me check if you understood this. Thermal decomposition of calcium carbonates, we have here calcium oxide plus CO2. This is just a gas and this is solid and this is also solid. Can you predict if the heat change here for forward reaction, is it positive or negative? Watch it. If you heat this more, you will get more of CaCO and CO2 will come out. The more you apply heat, the more you favor this side. And any reaction that is favored by more heat is endothermic. So which means the thermal decomposition of limestone is an endothermic what? Reaction. But you combining CO2 and calcium oxide should be exothermic. You understand it now? So you can predict them. This is just a little cheat by checking. If I keep heating this, will they be favored? Anything that when you know you apply more heat, it will not be favored is an exothermic reaction. Because exothermic reactions, heat are released and no need of heating what is hot again. Let's take it that way. Okay, coming to entropy change. Entropy is the degree of disorderliness of a system or the system's inability to do work, depending on the angle you are coming from. So we have that we have solids, liquids, and gases. So these three states of matter. Solids, what I'm having now is marker, is a solid. It's highly arranged, it's ordered, and that's why I'm writing with it. This board is solid, it is ordered. But water is not as ordered as solids. Water will only be ordered depending on the container. You cannot tell me this is the shape of the gas you produce. Maybe in the classroom or anywhere where you mistakenly fart, you produce a mess there. You can't tell me this is the size or this is the shape. So gases are highly disordered. So gases have the highest entropy, followed by liquids. Solids have the least entropy. Then for your exams, change of gas to liquid means decrease in entropy. If a gas changes to liquid, and that's what we call, change of gas to liquid is called condensation, if I'm right? Yes. Change of gas to liquid, they will ask you the entropy change, will it be negative or positive? If a gas changes to liquid, the gas now is the reactant. We take it as the reactant, it started there. Then the liquid is the product. And remember that I told you that liquids have less entropy than gases. Let's just use an arbitrary number. Let's assume the entropy of solid now is 1. That of liquid may be 5. That of gas may be 15. We just assume this number. Then change of gas to liquid, the entropy change, entropy, will it be positive or negative? To answer this, when gas changes to liquid, gas is the reactant, then liquid is the what? Product. So in this case, the entropy of liquid, which is the product, that's delta S is equal to entropy of product, which is this liquid, 5 minus the entropy of the reactant, which is now what? 15. If you do this, it becomes what? Minus 10, which means entropy change is negative. In other words, the entropy change has decreased. That's the meaning. There will be decrease in entropy change. Any questions so far? Okay. there will be decrease in the entropy what change. Now, which means condensation entropy decreases in condensation because you are changing gas to liquid. But evaporation, that is where liquid will change to gas. Evaporation entropy increases in evaporation. If it is evaporation, it's all about changing liquid to gas, so that we have 15 minus 5, it becomes 10, which is an increase. So then you change of solid to liquid, an increase in entropy, so it's going to be positive. Entropy change will be positive because there is an increase in that aspect. So what do I mean? Melting, entropy is going to be positive, but freezing, entropy is going to be negative. Freezing, negative. Then if they set these temperatures for you and tell you ice at 0 degrees, the higher the temperature, the higher the entropy. Simple. Then water at room temperature, then steam at 100 degrees, then even if it's not at 78, it is water that is the answer, class. Steam, the higher the temperature, the higher the what? Entropy. So we can see, as far as thermodynamics are concerned, so free energy is used to determine the spontaneity of a given reaction. Spontaneity. So here is our Gibbs free energy. Gibbs free energy. Then here is our heat change, as usual, you know it here. Then here is temperature in Kelvin. If you don't want to put Gibbs, you just say free energy. We have heat change. Then T here is temperature in Kelvin. Then, as usual, this is entropy change. Now, in this situation, the Gibbs free energy is used to determine the spontaneity. What do we mean here? Spontaneity of a reaction is determined by the value of change in free energy. Whether a reaction will proceed on its own, whether it requires external energy before it proceeds, or whether a given reversible reaction is at equilibrium, it is determined by free energy. Summarily, change in free energy, when after solving all this for a given reaction and they give you a value that is positive, that's when the value of free energy, which is positive, it shows that that reaction is non-spontaneous. Non-spontaneous, meaning such reaction do not naturally occur. You must add external energy, maybe like heating, to force it to start happening. But when free energy, the product is negative, the reaction can occur on its own. It is spontaneous. You heating is just to increase the rate of reaction. For something to proceed and rate is not the same. So when free energy is negative, the reaction is spontaneous. Then when free energy is actually 0, it shows that for reverse equilibrium, for reversible reaction, it is at what? Equilibrium. So I wait for some of your questions in the thermodynamics. Heat of formation, you give me a question on that and I'll solve it for you and tell you the way out by the grace of God. So I continue with the ones I have here till you give me another question. Explain briefly the following terms using an appropriate example. Using an appropriate example in each case. I should be homologous series. Homologous what? Series. Then next one is heterolysis.
Laws of electrolysis.
Kind of monetization.
I don't know.
Guys, you check the video concerning first Faraday's law of electrolysis. I'll give you that brief here. I did not treat Faraday's laws of electrolysis. Remember, this man, Michael Faraday, don't have much formal education. So I always use this man because I think I like him. He's my model. He was able to combine religion and science, and none cheated the other. Unlike today, where big scientists may get it confused about God. And some religious people don't even know what science is. They keep quoting. But this man combined religion and science, and none of them confused him. He has a little formal education and was a student of Humphrey Davy. So I'm just using this man to give you morale, to start thinking practical, to avoid religion from stopping you from being a scientist. So, and to stop using religion to confuse science also. So this man merged the two. With his little formal education, he was able to put a law that guides electrolysis. But Davy has been using electrolysis some years ago, but he couldn't put this law together. It was Humphrey Davy that discovered potassium. He started sodium and potassium. But this talented man and focused came with a law. We have first and second law. The first law is very simple: garbage in, garbage out. If your input is high, your output will also be high. I say that the quantity of electricity supplied, or rather that the mass of an element discharged, is directly proportional to the quantity of electricity you supply. Simple. If you have more electricity, there will be more mass. If you have less electricity, there will be less mass. That's just it. Then, in that case, M is for mass, Q is for quantity, where quantity, unlike maybe if you measure rice or beans, you say 2 cups of rice, 2 cups of beans. This time around, how do you measure electricity? The flow of that current. In other words, Q is equals IT. In that case, you can now substitute Q with IT. Then we have that mass of element discharged is directly proportional to the current and the time of flow of the current. That's just the first law. The mass of elements discharged at the anode and the cathode during electrolysis is directly proportional to the current and the time of flow of that current through the molten or solution form of that the compound of the element in question. So in this case now, to remove sign of proportionality, we have to put a constant known as electrochemical equivalent. So M equal to EIT. So if you master the electrochemical equivalent, you can also watch my video here on cheats on exam. Every element has its own electrochemical equivalent. If you master it, you can use this and solve your questions. Then for that, call that mass, Ramit over Jaffa. That's the whole thing you calculate concerning first law. This will help you get the answer correct. Even calculate for charge present. Sorry, calculate for charge present. That's the advantage of this formula, because all these ones that we teaching you will not enable you calculate the charge present, but this one will enable you calculate the charge present. So mass discharge is equal to Ramit over Jaffa. This is Majesty's cheat, made and forged by me, tested and trusted. It will give you answer. Now, RAM means relative atomic mass of the element in question. If you are talking about copper 5 or 64, if you are talking about aluminium, here should be 27. Then this I is current in ampere. Please don't joke with the units. I, current in amperes. Then T, time in seconds. So Ramit over Jaffa. Ram means relative atomic mass of the element. I means current in amperes. Then T means time in seconds. Then char here means charge. The charge present on the ion of the element. If you are talking about sodium, you use 1 here because sodium have +1. If you are talking about magnesium, you use 2 here. If you are talking about aluminium, you use 3 here. If you are talking about copper, you use 2. Zinc, you use 2. That's this charge. Then Fa here means 1 Faraday, which all of us know that 1 Faraday is equal to 96,500 coulombs on approximation. But when you watch the video on the first law of Faraday, you find out that this is not exactly the value, but just estimated. There is a new value for that. But when you use this, it will work out. So that's the only thing I'll tell you when whenever you use this, it will work out. So if you are asked to calculate for current, you make I the subject of the formula by saying now what? That Ramit is equal to mass times Chaffer, because they will give you mass and T, leaving I alone. So that what we have here, RAN over T, such that times charge times 1 Faraday all over relative atomic mass times time in second. Try this, it will work out. Then second law is where I will help you. Maybe when I go down, I may see a question concerning law. If you try this method, it will work out, please. Then for second law, the second law is dicey. That's where students find it difficult. Even some teachers, sorry to say. That second law is somehow saying that we need to state it that when the same quantity of electricity is applied through different electrolytes in an electrolytic cell connected in series of electricity being applied on different electrolytic cells connected in series. Let's have the series connection here. Series and parallel connection is not the same. Your physics teacher will do good there. I'm only focused in chemistry and biology, then medical courses. So, but I know your physics will tell you what we mean by series and parallel connection. So if here is plus, here is minus, the next is plus, this should be negative. So that connection from here to here is the final connection. Then other ones moves this way from negative to positive. So let's assume that this one contains AgNO3 and this one contains copper 2 tetraoxide as the electrolyte inside it. Remember, electrolysis is the compound or the substance that you really want to electrolyze, you want to break down. And here is an aluminium chloride molten. Taking it that there is no water, they are all molten. But where our interest lies is on these ions. This is Ag plus, Cu2 plus, and Al3 plus. So when the same quantity of electricity is applied through different electrolytes, as you can see, 1, 2, 3, connected in series, that the number of moles, class, you should note this, we are talking about moles, not mass. The number of moles of the elements discharged is inversely proportional to the charge. Second law of Faraday, if you have your pen there, states that when the same quantity of electricity is applied through different electrolytes in an electrolytic cell connected in series, as you can see here on the board, that the number of moles and not mass, number of moles of elements discharged at the electrodes is inversely proportional to the charges present on the ions of the elements in question. We are talking about inverse here, which means that the higher the charge on the ion of the element, the lesser the mole discharged, because it's inverse. Is equal to 9, such that x is equal to what? 27. This 27 that have one charge, which means if 9 ion was discharged, of sodium will be discharged, 27 moles of potassium will be discharged, because they all have +1. Just use this my cheat. Then here, the original should now be the inverse of 2 is 1/2. 1/2 times the original, which is our 20 charge of copper, which will give you about 13.5 moles. So what do we have? 27 moles, 13.5 moles, and 9 moles. If you move from 27 to 13.5 to 9, you are decreasing. But look at their charges. Their charges is increasing. +1, 2, 3. So the second law is showing you where you can of silver was given. Can you access that of aluminium? Let's assume if you are told that 0.1 or let's say 0.5 moles of silver was discharged by a given quantity of electricity, what mole of aluminium will be discharged? You still take the same thing. It's very simple. This is plus 1. The inverse of 1 is 1. Simple. 1 over 1 times x is equal to 0.5, such that our x is equal to what? 0.5. So very simple. If you come here, the number of moles of copper that will be discharged is 1 over 2 times this 0.5. Remember, when I started here, I used 1 over 3 times x unknown. But when this silver was given, you just say, because the charge is 1. Remember, I'm not restricting this to silver. Any other ion that have plus 1 follows that rule. Sodium plus 1, potassium plus 1. So for the plus 1, you just say 1 over 1 times x is equal to, because this was the mole given, such that your x is 0.5. Simple. When you now come here, it becomes 1 over 2 times 0.5 will be discharged, which is dividing 0.5 by 2, which will give you 0.025. Am I correct?
Yes.
Okay, we'll give you 0.025. Then the mole of 5, which will give you a lesser mole. So in this second law, that's the only way students may find difficult. But I hope with this explanation, someone will get it correct. Let me just solve a question there. If they tell you that during electrolysis, that a given quantity of electricity discharged, let's say discharged the 2.5 moles of silver. Calculate the mass. Calculate the mass of copper that will be discharged by the same quantity of electricity. Discharged by the quantity of electricity. So share this particular good thing. Anytime you come across this my class, if it is helping you, let others know about it. Please spread the light. Some Majesty's World Science Channel is good for you and for your friends academically as far as science is concerned. You can also place your adverts. You have the number where you can reach me on WhatsApp. We have +234. If you put it, if you are calling from outside Nigeria, 651662117. You can place your adverts there. This is the number you use to reach me. Then for further studies, as far as science is concerned, I can give it to you. I can private live stream with you, be your private tutor, despite wherever you are here on earth. As far as YouTube is concerned, I will locate you. So God bless you. Don't forget to subscribe. Now, back to what we are saying. Now, the question says 2.5 moles of silver was discharged. They now ask you what mass of copper will be discharged by the same quantity that discharged 2.5. Solution to this. The solution first, you have to grab your first law, and before grabbing that, you should know that there is difference between mole and mass. Class, look at it. They said 2.5 moles, and now they are asking you mass. First, you have to go and find the equivalent mole of copper that will be discharged when 2.5 moles of silver is discharged and convert it to mass. Listen, find the equivalent mole. As I taught you now, I use 0.5 and I use 9. Find the equivalent mole of copper that will be discharged when 2.5 mole of silver is discharged. So having the idea of that silver is +1, copper is what? +2. We are using inverse. Here is our inverse is 1 over 2, and here is 1 over 1. So they have told us that our x already, because 1 over 1 times 2.5 will still be, that's 1 over 1 times x. Let's assume the final mole is what we don't know is equal to 2.5. You will still land by that x is equal to 2.5. So if we 1/2 of the X you calculated. So the number of moles of copper, if 12.5 moles of silver was what? Discharged. What mole of copper will be discharged? 1/2 of that of silver that was discharged. Simple. Of copper will be what? Discharged. So half of 2.5, what is that calculator? 1.25 also. 2.5 divided by 2. 1.25, of course. 1.25 moles of what? Copper. But they asked you mass. Then you go back and convert mole to mass. Remember, they will also give you in bracket for Nigerian exams is 3.5. But for GSC, that's Cambridge, they will not give you anything. Rather, behind the book in the question paper, you see a periodic table which contains the mass number. So it now lies on whether you know what to use. So having known that copper is 63.5 or 64, what does it mean? That 1 mole of copper is 63.5. Then 1.25 moles will give you what? It will give you now do your normal cross multiply now. So what do we have? We have now that 1 is 63.5, 1.25 is what? X. 1.25 is nothing but 1.25 times, yes, of course. So that X is equal to 63.5 times 1.25. So our calculator here, from the calculator department, we have times 63.5. So we have 79.4 grams on approximate our answer. Then take note from the question I cleaned, they said 2.5 moles of silver was discharged. Where students are usually tempted, if this mole was changed to mass, 2.5 grams of silver, if they change this mole to mass, class, you dare not go back using 1/2 of 2.5 because the law says it's inversely proportional to mole and not to mass. Take note, if this mole was converted to mass, like in that question I said a given quantity of electricity discharged 2.5 grams of silver, not mole. Calculate the mass of copper that will be discharged. Don't use this relative. First, convert this mass of silver to mole. When you convert it to mole, you now use this. And 1 mole of silver, actually, we have that mole is equal to Rm over N. That's reacting mass over molar mass. Any questions so far? Okay. If there is no question, that means God is working. So remember, I can't see myself, I just reflect how my class moves. So reacting mass here is 2.5. Molar mass of silver is 108. From the calculator department, you have 0.023. Correct. 0.023. It is this that we will now use and go and find 1/2 of it. You now divide this by 2. Whatever it gave you, you now convert it back to the mass of copper for you to get the real answer. That is it for Faraday's law of electrolysis. So we continue with some of the questions we have here until we ask another one.
Someone said preparation involving specific gravity.
Preparations involving specific gravity. This one is not, this is more like we are here in theory, you are more like a practical question. Please, I know your question is coming from the idea that you want to learn how to prepare some solutions from a stock solution in your lab. You can watch my video here on WAEC Titration 2020 or Titration Guide for any teacher. You listen well to that video, you will understand. That is more practical than theory. And there are some calculations there that you will only gain when you are working with me in the lab or you are my private student. It's somehow that, but just know that the specific gravity, remember that SG have no units, but it reflects relative density. So they are comparing the density of that particular thing with that of water. That's relative density, which is what we call SG. Of course, density has a unit, but relative density don't have. So if they tell you that the density of a liquid is 1.8, which is for HCl, it's just trying to tell you that you know the percent that is of the acid and the percent that is of water. Relative density, or SG, goes with percent concentration, volume over volume, or weight by volume. So you should know that. That's the only thing I will say. I will entertain more questions that are more theoretical related, because we are here doing our theory and objective questions. Okay. Somebody say homologous series. They asked us to discuss homologous series. You know, homologs means similar. Homologous, anything homo is uniform, similar, and this is organic chemistry, and I hope we are very familiar with that. So homologous series is actually a group of organic compounds that follows a regular structural pattern. They follow regular structural pattern in which each successive member, that's a member after the other member, number 2 and number 3, number 3 and number 4, that's successive, number 4, number 5, in which each successive member vary in their molecular mass by 14, or molecular weight by 14, or in their molecular formula by a methylene group. By a methylene, they either vary with this or vary with 14, because this converted to mass is this. Carbon is 12 plus 2, 14. So one common feature of them is that they say the characteristic is this: they have to follow a regular structural pattern, meaning all of them obeys what we call, they have general molecular formula they follow, like alkane, alkene, alkyne, the alkanals, otherwise known as the aldehydes, the ketones, that's the ketones, otherwise known as the alkanones. All of them are homologous series. It's just like a family, like you have your family there. There are things that unite you people, and you people are not exactly the same. At least you vary by age. I trust some families, they do their spacing well. So at least that question has been tackled. Is there any other question so far? Okay. So as I wait for your question, we go on, and please remember that ask your questions. Okay. Then some people, just to demonstrate what I've just said, if you come to methane, you have, that's alkanes, so that you understand this definition of a homologous series. The first member of alkane is CH4. Second member is, if you want to find the next member, just add CH2 to the other member above, which means we have one C, add another C, it becomes C2. We have 4 hydrogen, add extra 2, it becomes H6. So next member, C2 plus 1, C3. H6 plus 2, H what? 8. If you come to alkanols, the first member, let's take it as CH3O, that's methanol. For you to get the next member, just add this CH2. So we have 1 C already, add another C, it becomes C2. Then we have 3H, add another 2H, it becomes 5. OH is constant because that's their functional group. Then the next member, can you predict what it will be? C2 plus 1, it becomes C3. H5 plus 2 becomes H7 and OH. So we have here methanol, ethanol, propanol. So it is applicable for any other homologous series. That's why we say each successive member vary in their molecular formula by a methylene group, that's CH2. Why I put this is that it cannot be free. It's not in existence or on its own. It must be a mass is simple. Carbon is 12, hydrogen is 4. 12 plus 4 is what? 16. 16 plus 14 is 30. For you to get this next one, 30 plus 14 is 44. If you doubt, you now count. Carbon is 12. 12 times 2, 24. 24 plus 6 is 30. So next member should now be plus 14, which will give you around 58, of course. So that's what they mean by that. Okay. That's for homologous series. If you are not satisfied with it, you let me know. Going to the next question. They say state the indicators which could be used to determine the endpoint of the following titration. Dilute hydrochloric acid against sodium hydroxide solution. Please, this is all about choice of indicator in titration. And remember, litmus is not suitable for acid-base titration because of its pH transition range. Because of its what? pH transition range. I know in your school what you encounter is litmus paper. I need to tell you that we also have litmus solution. Just stay subscribed. When I'll carry out an experiment on fountain, that's fountain experiment, you know that we have litmus solution. So litmus is an acid-based indicator but not suitable for titration. So don't even put litmus in acid-based titration because of its pH transition range. Maybe if we keep advancing, you'll understand what I mean. That's the reason at which they change color. It's not suitable. Then, choice of indicator during titration. Choice of indicator during titration. I'll teach you salt hydrolysis and we may end. I think how many minutes so far?
1 hour 11 minutes.
Oh, okay. 1 hour 11 minutes. Okay, at least maybe we'll just do 1 hour 30 minutes. We'll wrap it up. Choice of indicator during titration. If you are titrating between strong base and strong acid, B base, A acid, please. Any indicator can serve. Any indicator, but I don't think litmus is permitted. Any indicator, which means methyl orange, phenolphthalein, conjo red, methyl red, and many other indicators. Then when the titration is between strong base and weak acid, good example is when we are titrating sodium hydroxide versus any organic acid. Let us say ethanoic acid, C3COOH. This type of titration, the choice of indicator is phenolphthalein. When acid is weak, you use phenolphthalein. So phenolphthalein is the most suitable in a titration between strong base and weak acid. Then a titration between a weak base and strong acid, you use nothing but methyl orange. This is where methyl orange is applied. When the base is weak, such titration is titration between aqueous ammonia and H2SO4. If you do titration between aqueous ammonia, otherwise known as ammonium hydroxide, versus H2SO4, methyl orange is suitable. Understood? Then the other one is opposite of the first one, weak base, weak acid. No suitable indicator. So such titration becomes practically not visible. So when we have weak acid and weak base, please, no suitable indicator. I don't know what's happening to our marker. So that's it for choice of indicator. That's what they are trying to let us know. So if you are titrating in class, dilute hydrochloric acid against sodium hydroxide, that is strong base, strong acid, you can use any indicator. Then the other one says dilute hydrochloric acid against ammonium hydroxide solution. Just like this, but you replaced it with HCl here. You use methyl orange. Then if the titration ethanoic acid against sodium hydroxide, you use phenolphthalein. Whenever the acid is weak and base is strong, phenolphthalein is suitable. Remember, phenolphthalein is a laxative. Don't joke with it. It purges. I'm talking from experience. So it's a drug also. It causes purging. So it's somehow not too good. And you know the color. You can watch a marriage proposal with chemistry here in this channel to see the magic I used these indicators to perform, where you can use chemistry to propose. So I educate and I also entertain. Then the other one is ethanoic acid against soda hydroxide. I've answered that. The answer is phenolphthalein. Then another one is acid trioxocarbonate for titration. That's HCl versus potassium carbonate or sodium carbonate. Please, methyl orange is suitable. acid triazocarbonyl titration, methyl orange is suitable. Then it's just maybe my mind is just trying to tell me to teach you salt hydrolysis. Remember, I'm waiting for your questions, please. Okay. The hydrolysis of salts, salt hydrolysis. So you know hydro, water, lysis, breaking down. Just what happens when salts react with water or when they are dissolved in water. Most often they will ask us which of these salts will dissolve in water to produce a pH equal to 7, pH less than 7, pH greater than 7. The way to answer it is by salt what? Hydrolysis. I've taught you choice of indicator in titration. We will now use that same thing. A salt formed from strong acid and strong what? Base. If a salt formed from strong base, strong acid, or strong, do not hydrolyze. Do not hydrolyze. Rather, they will give us a pH of 7 exactly. Then, good example is this: sodium chloride. How will you know the acid and base that forms sodium chloride? Simple. First, remove the metal. Replace the metal with hydrogen. Then leave the non-metal. You have gotten the acid. I've removed the metal, no matter the salt, just remove the metal or the positively charged ion there in case of ammonium salt. Replace it with hydrogen. Keep the non-metal constant. So the acid that formed this is what? HCl. Then for you to see the base, remove the non-metal or the anion, replace it with OH. Allow the sodium to remain. So this sodium chloride is formed from HCl and sodium hydroxide. HCl and sodium hydroxide. This is a strong acid and strong base. For the benefit of this class, just note this. It's like marker is ending. I think I will use that iPad. You know, can you get it like this? Please, since marker is disappointing, see, for the benefit of this class, we have NaOH. These are strong bases. KOH, all strong base. There are other strong bases. Then for acids, HCl, HNO3, H2SO4. These three for now. There are other stronger acids like the hydroiodic acid and many of them. These are strong words. Acids. Then when we say sodium chloride, if you dissolve sodium chloride in water, it will give you a pH of 7. Why? Because it's a salt of strong acid, which is HCl, and a strong base, which is sodium hydroxide. Understood? So a salt of strong acid and strong base do not actually hydrolyze, and they give us neutral solution. Another one is salts of strong acids and weak bases. Please, the strong one wins. Strong acid and weak base, they will hydrolyze. This one hydrolyzes. We hydrolyze in water. We hydrolyze to give a pH, to give a solution of pH equal to what? A pH that is actually strong acid. You know that acids have pH less than 7. Yes, pH less than 7. Good example of such salts is ammonium chloride. Ammonium chloride. So you remove this, or even aluminium chloride. Just remove the cation, place hydrogen there. So what do we have? HCl. Then keep the cation constant and remove the anion. So what do we have? NH4. So this ammonium chloride is a salt of HCl and ammonium hydroxide. HCl here is a strong acid. Check this, ammonium hydroxide is not there, so it's a weak base. So this is a salt of strong acid and weak what? Base. So which means if you dissolve ammonium chloride in water, it will turn blue litmus paper red because it will have a pH less than 7. That is it for salt hydrolysis. Then the next one is a salt of weak acid and strong base. We have a pH greater than 7 because base will win. Remember, bases have pH above 7. Good example of such salt is sodium ethanoate or sodium oxalate. Sodium ethanoate or sodium oxalate. So in this case, how will you know the acid that formed it? Just remove the metal and put H. So the acid is CH3COOH. I say remove the cation, replace it with hydrogen. Then how will you know the base that formed it? Then the sodium is the cation, then put OH there. So this is a salt formed from these two. So not the least, salt of weak acid and weak base. Weak acid, weak base. That's a salt of this formula is this scientifically correct? Don't think. Ammonium carbonate. This is a salt of weak acid and weak base. Remove the cation, put H, it becomes H2CO3. This is a weak acid. Then, how do you know the base? Remove this one and now put OH. So this is a salt of weak acid and weak base. Please, this one will not hydrolyze. So salts of weak acid and weak base do not hydrolyze, which means they have pH equal to 7. So this is how we come to the end of today's class. It is very good to know that you're there, and I hope this class will help you in this forthcoming examination. So don't fail to tell your neighbors that Her Majesty's World Science Channel have the answer to your problems in chemistry. And I can't end this class without thanking my engineer. He came all the way here. He traveled, but thank God he's back. I thank him, Engineer Chinonso Oba. He has been there, my backbone. Thank him so much. So God should bless you for being there. Please expand this science community. I am a kind of there for you wherever you are there for me. This live stream will hold if you want again, maybe in biology. God bless you and remain blessed.